Example of how to build and boot into a Zen system with a fit image, and then go into the benefits of why you even want to use a fit image. So first, a little background on U-Boot. U-Boot is an open source bootloader, which is the initial program that loads the software your system needs to run. The project's origin is a 8XX PowerPC bootloader called 8XX-ROM, written by Magnus Dam. In 1999, Wolfgang Dent continued the project and renamed it to PPC Boot. In 2000, PPC Boot was released to the public, and then in 2002, it was forked into a product named ARM Boot, but then was just merged back into the PPC Boot project shortly thereafter. And now, since it had multiple architectures, it was renamed to DOS U-Boot, or the Universal Bootloader. More architectures have been added over time, and then in the early 2008, flattened image tree support was added. So U-Boot has quite a few features. It provides many loading methods, including from MMC devices, flash devices, and over network. There are a ton of supported architectures that are all still being maintained, and it also provides file system handling for many different file system types, including all versions of EXT, FAT, UBIFS. And there's also network handling, so you can do pinging or TFTP files over. And then you can also perform direct memory reads and writes. So, for example, you can do NAND reads and writes, or SF read. So now a little background into the fit image. The fit image uses a tree-like structure that's similar to a device tree, and it generates a single binary that includes all of your images for booting. For example, your kernel, a RAM disk, and an FDT. So the fit image provides some benefits over the other booting methods that U-Boot provides. Mainly, this is hash checking on the images and having multiple configurations at boot time. I'll expand on more of these benefits later. While the fit image added flexibility and convenience to U-Boot, it lacked the ability to boot more than a single kernel, which prevented us from using it on Zen systems. So the build requirements for a fit image, it requires the make image utility that's built along with U-Boot and device tree compiler. Then you also need all of your binaries for your system. So that would be DTBs, kernels, optional RAM disks, and optional loadables, which again was our new contribution. And then you need an image source file, which generally has the .its extension. That's your device tree-like source file. So when generating a fit image, the image source file references and defines all of the images that need to be in the built FIT image. So the make image utility then uses the image source file and all of the binaries that the image source file references and generates the single FIT image, or usually .itb file. So the fit configuration, the image source file before our updates. Here's an example of an image source file. So as you can see, it looks very similar to a device tree. At the top level node, there's the requirement for a description and address cells. Then all of the images are defined under the images node. So if we take a look at the first image defined, that's your kernel. It's just arbitrarily named kernel at 1. There are quite a few fields highlighted. These are required for all images under so that would be a description, which is a human readable explanation of the component. Data, which is just the path to the actual binary file. And there's type, which is the component type, and that can be either kernel, RAM disk, standalone, or flat DT. And then there's compression, and that's obviously the compression method for the components. That could be gzip, bzip2, or none if it's not compressed. And then there's some required types, or there's some required fields for certain image types. So there's OS, which is the operating system name. That's only a requirement for if it's a kernel. Then there's architecture. That's the processor architecture, so that'd be ARM or PowerPC or MIPS. And then there's entry and load, and those are your entry address and your load address, respectively. And then there's the optional hash node that you can define for each image. And each image can have 0 or more hash nodes. And the required properties for that is the algorithm. So that could be CRC32, MD5, or SHA-1. And then optionally, you can provide the value yourself for the checksum. If you don't provide it, then when the fit image is compiled, it automatically calculates it for you. So as you can see here, we have a single Linux kernel defined as type kernel and 2 FDTs defined as type flat DT. Continuing with the example, we finished defining all of our images. There's also a RAM disk now. We now move on to our configurations node, and the required properties for that is, again, a text description, and a kernel image, and then a device tree or FDT. So these just reference the images that were already defined above. Optionally, a RAM disk image can also be used. So as you can see, we have 2 different configurations. Both use the same kernel image. Configuration 1 uses FDT1, and configuration 2 differs by using the other available FDT and a RAM disk image. If you want any more specifics on the image source file format, you can follow this link. It's the U-boot documentation. So the loadables, which is a new configuration property, is what DornerWorks added. So again, our problem, if we wanted to load a Zen system, we need to generate a fit image with a Zen kernel, a DTB, and a DOM0 Linux kernel. So the kernel, FDT, and RAM disk configuration properties can only have 1 image per configuration node, and U-boot performs specific tasks and checks based on the image type. So when trying to set up a configuration for Zen, the kernel configuration property is what gets executed. So that needs to be the Zen kernel. The FDT property needs to be our device tree, and the RAM disk property can't be used for a DOM0 because U-boot checks to make sure it is a RAM disk, and also a user might want to actually use a RAM disk. So this leaves us needing something new so that we can load a generic image just to a location and then leave it alone. So what we came up with was with an entirely new configuration property called loadables. The loadables is a list of some previously defined images. So from our previous example, that could be kernel 1. You could also just have multiple other files. You could have, kernel 1, kernel 2, and kernel 3 as your loadables. So the loadable property just performs any defined checksums and then loads the image to the defined load address. No extra tasks or checks are done. Obviously for Zen, we only need the DOM0 kernel, so we only needed 1 loadable, but we saw value in allowing it to be a list of multiple images, just since it was so generic in the first place. So we added that as well. So doing the actual updates, we made the changes to U-boot, trying to follow their design principles as shown to look for the new loadables node, parse the node, find the images it references, and then move these images to their respective load addresses. We then refactored some of the involved functions to improve readability and code simplicity, and we also added a test for the fit image with 2 loadables, so that runs a sandbox test when you do a make test. And our changes were added to U-boot mainline and can be used at or after the tag v 2015.07. More changes that we had to do were changes to the make image utility that's included in the U-boot source. This change, now when you generate your fit image, it actually tells you about your loadables. So you can build it with an older make image and it will construct it correctly, but it won't give you any output about loadables, so you might be a little unsure if it actually did it or not. So as you can see in this example of output, we see that the Linux kernel that we define is now a loadable. So this change was introduced with the other one, so you'll generally want to use a make image built on or after that same tag. So here's a full example of a source image tree for a Zen system now that loadables is implemented. Here you can see we have our Zen kernel defined as type kernel, and we have two FDTs defined. One is for use with Zen, and one is for use without Zen. We also define our Linux kernel. We also define it as type kernel, and then we have two configurations. The first defines the Zen kernel as the kernel, then the Zen device tree as the FDT, and the Linux kernel as a single loadable. The second configuration uses the Linux kernel as a kernel and the non-Zen device tree as the FDT. So this would allow you to choose configuration 1 to boot into Zen, or to choose configuration 2 to boot into plain Linux. In this section, I'll give some examples on how to build and boot a fit image on your target. So first things first, you will likely need to build your own U-boot. Most configurations don't enable fit support by default, and likely the newest version with our patch wouldn't be in a pre-built binary. Then you build all the images you would normally need, so your kernels and your DTB. Your device tree will be a little different than how people booting Zen normally do, where you just use your DTB that Linux provides and then modify the chosen node in U-boot, just because it's a little harder to interact with your FDT when it's coming from the fit image. So what I did was I generated an FDT where I already filled out the chosen nodes. Then you're going to move all of your built images to the location that the fit image source file specifies, and then build the output fit image with the make image utility. For QB-Truck, which is what we used to do this testing, we used an SD card for booting, so after all that was done, we copied the U-boot binary and the fit image into a boot partition on the SD card. So now booting it, we started up the board with serial connected and the SD card inserted. We halted the auto boot of U-boot, and then we loaded the fit image into memory. We used fat load MMC because the fit image is on a fat partition on our SD card, and the memory location we use is a section of RAM that won't interfere with where any of the images will need to get loaded to. So to boot a configuration, we use the bootm command with the address at which we loaded the fit image, followed by a # and the configuration we want. If you want the configuration that's specified as default, then you can just do bootm with the fit image address. So once that occurs, U-boot will then perform any hashes specified for the images in the configuration, and then the images are moved to their load addresses, and the Zen kernel starts booting. Also, as a side note, if you need any information about your fit image, you can use the iminfo command and provide where you've loaded the fit image, and it will basically spit out what your configurations and images are for you. So here's an example output when booting the fit image. As you can see, it gives you information about each image in the selected configuration. So it mentions our selected configuration is config 1. Our selected kernel is the Zen kernel. You can see it gives information about the compression, side, load address, entry point, and all while it's booting. It then verifies any hashes for that image, so you can see that it looks at it, it checks the MD5 sum, and then says that it's okay. So it continues along. After each image has been tested, all the images get loaded to their load addresses. Then it starts execution of the Zen kernel, and you can see at the very bottom that you start seeing the output of your Zen kernel. So the benefits of using the fit, there are both things that everyone that uses a fit image benefits from, and then there's some Zen specific ones. First off, one of the main benefits most people why most people use the fit image is the ability to for hashing images. So this provides a few great uses. First off, you can make sure that none of the images were corrupted when the image was transferred to memory on the target. Another benefit is that you can manually specify a hash for your image. This way you only provide the exact image that you expect. This is useful for production environments that may be expecting a very specific version of images for its system. Lastly, another benefit for production environments is verified boot. This allows you to use a SHA-1 hash so that only trusted targets can boot your image. Another benefit is that it allows for multiple configurations, which kind of makes U-boot a little more similar to Grub2 if you've used Grub2 when booting x86. It's still a little different, but it makes it much more simple to try and switch between configurations, because all you have to do is just say, oh, I want config 1, which boots into Zen, or I want config 2, which boots into just plain Linux. Another benefit, a little more specific to Zen, is that you could also have multiple device trees defined. So all of them would be, all of your configurations would be booting into Zen, but you could have different device configurations such that maybe one configuration you want to pass through Ethernet to a guest, but then another configuration you just want to leave the Ethernet available to DOM0. So that would allow you to do a quick switch between those options. Another benefit is improving support, and this is one of the main reasons we wanted this functionality for Zen. Since DornerWorks will be providing support and a distribution for Zen on the Xilinx Zinc UltraScale Plus MP sock, we thought a fit image would give us another data point onto a user system. So one of the first things we can do is when a user calls up with an issue, we can ask them for their image source file, and we can get an idea of what configuration they're going for. And then it also allows us to provide sample known working configurations much more easily. We don't have to give instructions on how to where everything needs to get loaded. Say, okay, now halt the auto boot and load this image here, load that image there. It's all contained in that image source file. So that's something where we can provide that to users through the distribution. And then also anyone else who would be interested in doing something like that. So like the Mirage's Zen ARM builder could have different fit configurations already set up for anyone who's using that. And then there's also some other benefits we think that this change can facilitate, but would require further changes to U-boot or Zen, and would just require some more research. So this would be loading more of your images at boot time. So loading images for coprocessors or FPGAs or loading databases or even loading your DOM-U kernels. All of this mostly just to improve your boot time, but likely wouldn't be possible to do as things stand now. So if you want to try it yourself, we actually did all this work on the QB truck and forked the Mirage's Zen ARM builder. So thanks for that useful useful tree. So you can feel free to give that a try if you have a QB truck. Otherwise, it's fairly simple, and as long as you use a newer U-boot, you should be able to try it on most any board. Any questions?
You decided to use different device weight for Zen and Linux based on your configurations. How do you think about in the future having only one way on creating new books, the different not of them? Because the main problem is that you have to fill yourself. The chosen node
Mm-hmm.
may require you need to know where you log into the memory, and you can't modify you can modify easily the Zen command line, etc. Because I may have did something, but how the Linux command line is passed with you? Is it directly on the
Oh,
Linux,
okay.
or
It's in the built device tree blob.
okay,
So what I did was I had two FDTs, or DTBs, one of which had my chosen node already filled out. So that had DOM0 boot args. It had location of where DOM0 was going to get loaded to.
what about in the current state, like you use your boot fix without them, the kernel? Where do you pass the command line? Is it on the U-boot script or is it in the U-boot fix?
I believe it's still in your device tree.
It's still in the normal place in the device tree where there's the, I'm trying to remember, I can't remember the name of it offhand.
No, it's like, yeah, it's like boot args or something.
You can't from the U-boot say, I want to modify the command line. Because when U-boot currently on the kernel on U-boot without U-boot tree, it's like
Right.
you put the command line on the
Mhm.
paper, on the environment variables.
I think you might be able to.
Okay.
I'm not positive. I haven't tried it.
I'm just looking at that because having two devices, it's like having two devices with something like a bit like more management for the user rather than getting something.
Hmm.
But I understand that's maybe difficult to modify the device in the woods.
Right. Yeah. Yeah. I think it's a little more user friendly to explain how you would modify it, just as source and then rebuild it yourself. But I think boot args and the way U-boot use boot args, I think if you're booting Zen, it applies your boot args to whatever U-boot is considering your kernel. So when you boot Zen, that's your kernel to U-boot. So I think you should be able to at U-boot runtime modify your Zen boot args. But your DOM0 boot args are within your device tree blob, and those you cannot modify.
I think our target with this was not so much, it's probably not something you use on a development machine or development board where you're like, it's more of a production environment where you've produced some image that you want the customer to use and you want them to be able to say boot config 1, boot config 2. It's not something that you're going to...
Or even like a jump start for users. So you can say,
like that, yeah,
here's a few different configurations. Here's one that's just running Zen, DOM0 gets all your devices. Here's a configuration where you're booting Zen, but you're passing through an Ethernet device, and it would then be abstracted out so that the user would just say, oh, I just have to boot config 2 if I want to pass through my Ethernet.
It's a good idea in general for like this solution because today we don't have a good way to say with you how to choose between Zen on the kernel.
Right.
So that kind of things would be very good.
Yeah, that's kind of what we were going for. Any other questions? All right, well, thank you very much.